All right, welcome back, everybody. We are going to finish off chapter 4 here. And the next thing I want to talk about is relating directly to cyclic alkanes. All right, and we've seen these pop up a little bit before, right? We've seen them pop up in nomenclature. I want to talk a little bit more about some of their actual physical conformations. So, in a way, this is kind of similar to Newman projections. We're sort of looking at a deeper model of how these cyclic alkanes actually exist. All right, so whenever we're drawing them like on a piece of paper to show like a reaction or something, then we pretty much just typically draw them as polygons. All right. There's cyclopropane, looks like a triangle. We have cyclobutane, square. Cyclopentane, pentagon. Cyclohexane, hexagon, so forth and so on. We could keep on going with this. All right. However, these really aren't very good representations for what you actually see, because there would be big problems if these guys actually existed in these different shapes, in these different planar shapes, right? And it's because of something called angle strain. Okay? So if you look at, all of the carbons in all of these structures, right, you would determine that they're all going to be sp3 hybridized. And that means all these carbons should have bond angles of 109.5, right? They're all sp3 hybridized. They all have 4 bonded atoms. That means they're tetrahedral. Tetrahedral has a bond angle of 109.5. Right. Well, if you look at the actual angles that are kind of represented on some of these, they're pretty far away from 109.5, right? This, right over here, this angle, that's probably about 60 degrees. In a square, of course, that angle's going to be 90 degrees. Pentagon and hexagon, the cyclopentane and the cyclohexane are a little bit closer, but they're still a little bit off. They're still not going to be able to quite get to that 109.5. The bigger the difference in the actual bond angle and the desired bond angle of 109.5, the more angle strain that we have. And that makes the ring more and more unstable, right? The closer it is to 109.5, the more stable it is. So, one thing that we see with these ring structures is that they actually don't exist in a two-dimensional plane. They will you have the rings, but they'll sort of try to twist and pucker, sort of contort their rings to try to make a more optimized bond angle. Okay? So, what we're going to do is we're going to see an example of how this happens. And the classical model is going to be with cyclohexane. All right, so that's going to be the one that we focus on. This does happen with all cyclic alkanes. Like I said, this is the one the model is usually based off of. They're all a little bit different, so you don't see necessarily exactly the same shapes with cyclopentane, cyclobutane, etc. that you see with cyclohexane, but this sort of gives you a good idea of what's going on. What you really want to concentrate on, though, is cyclohexane. That's what you're going to need to know about, what you're going to need to answer questions about. All right, so this is cyclohexane. As you can see, this is just a hexagon, just a flat hexagon, right? Well, actually, like I said, what happens is the ring puckers, and it actually exists more like this. And this is something that we call a chair conformation. And it looks like this. It looks kind of like a lightning bolt, right? Kind of looks like Harry Potter's forehead scar. It's called a chair conformation because it also kind of resembles a beach chair if you think about it, right? Let's say you're laying your back, against here, your legs and knees sort of go over this area, and then part with your feet bends down. So yeah, like a beach chair. That's why they call it a chair conformation. Okay? All right, let me redraw it. That's how we represent it on paper. You can also see, again on ChemTube 3D, here is a ball and stick representation, more of a 3-dimensional arrangement. And you can see, that this ring is definitely not planar, right? It's definitely sort of bent, puckered, contorted to try to get better bond angles. Okay? And so what you see right about here is a good representation of that chair conformation. Oh no, where did my whiteboard go? Well, this is awkward. I try to click back on it and it says installing. Let's see. La 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 la. It's coming. It's coming. I really don't want to start over, so I'm just going to sit here and talk for a few extra seconds while this thing loads. Anywho, what I was about to get to is what I just drew, the thing that looks sort of like a lightning bolt or a beach chair. That is going to be, there it is, that is going to be sort of the backbone. This is the carbon skeleton, right? We also have bonds that are coming up. Come on. That are coming off of each carbon, right? You know that each one of these carbons here is going to have two other bonds. And they look sort of like this. Okay? And there is a pattern for how we draw these, right? We have some of them that stick straight up and down. These are called axial bonds. And then we have others that are sort of slanted off to a side. These are called equatorial. And every carbon has one of each, has one axial and one equatorial. And for which direction you draw them, or as to which direction you draw them, there is going to be a pattern. Okay? For axials, you always draw them in the same direction as the carbon it's attached to. All right? So if we look at this carbon right over here, you see it's on a corner of the ring, and it's actually sort of going up. The corner carbon is pointed up. This is called an up carbon. All right? So if you have an axial bond on an up carbon, the axial bond points straight up. Okay? If you had a down carbon, such as this one, the axial bond goes straight down. Equatorial is the opposite. Equatorial slants in the opposite direction as the carbon is attached to, right? So, looking at over at the far right again, if we have an up carbon, that means this equatorial bond right over here has to slant and slant downward. All right? If we go over here, where we drew this axial bond, right? Down carbon pointed straight down, that means our equatorial bond has to go up and off to the side as a slant. Okay? Please, please, please get these straight. This is probably one of the things that people have the hardest time remembering, like on a quiz or an exam. They'll just simply draw their axial and equatorial bonds pointed in the wrong direction. All right? And honestly, that's a pretty simple thing to learn. But if you get mixed up on it, it can really kind of screw up your thought process. So make sure to remember that axial, straight up or down, same direction as the carbon. Equatorial, slants in the opposite direction. All right? So I'm going to draw another chair here. All right? If I were to draw all the axial and equatorial bonds for cyclohexane, it would look like this. And sometimes you have to, fudge a little bit because sometimes they're kind of sitting on top of each other. So I'm going to offset this axial bond just a little bit. My equatorial bond's probably pointing a little bit more up than I wanted to on this one, but I had to slant it, or I had to slant it a little bit steeper, but you can still see it's pointed off to the side. Axial, equatorial, axial, equatorial, axial, equatorial. And in cyclohexane, if we look at the atoms that are directly attached to these axial and equatorial bonds, well, they're all H's. So if I wanted to draw every little part of the structure, I would fill these in. Now, when you're working problems, you don't really have to do all of these axial and equatorial bonds. You can usually just focus on the ones that actually have larger substituents. But just showing you the overall picture, this is what it looks like. And if you want a much neater looking picture, we can go back to the chem tube diagram, and you can see we very nicely and neatly have axial and equatorial bonds hanging off of each one of these carbons. Okay? I definitely encourage you to go to this site. These little things, as you can see, are rotatable and movable. I'm doing it on an iPad right now, but you could also drag it with a computer. So either way. And if I hit the chair, I just touch the chair button and it goes back and resets it. Okay? Alright, so that's what a chair conformation looks like. Now, one thing that's kind of interesting is that once the ring gets into a chair, it doesn't actually stay there permanently. Alright, so I want to redraw my chair. Alright, what happens is this ring is constantly sort of puckering back and forth. It never really stops. Alright, so what happens is it sort of folds itself one way and then will fold the other way, and eventually you reach an equilibrium between them. Alright, so what will happen here is this chair will undergo something called a ring flip. So this is our chair, where it sort of goes inside out, and it makes this. This is a reverse chair. And it's literally, again, like if you had a beach chair and you're able to bend it, back and forth, it's like you're taking this back, this whole piece right here, the back of the beach chair, and sort of flipping it downward like that. Then taking the foot of the beach chair and kind of flipping it up like that. And that's how you end up with your reverse chair. All right, we can see this also in the ChemTube 3D, right? So here's our chair, right? If I click on the other chair, the one that's to the far right here, you'll see it's the same thing, same sort of zigzag, but it's the opposite. Chair, reverse chair, chair, reverse chair, right? It doesn't do it all at once either. It has sort of an intermediate process where one end has bent up and the other one has not. So that's called a boat conformation. This is sort of the in-between of a ring flip. Now this is only an intermediate. It doesn't last very long. Right? The two that are most important to remember are your two chairs. Okay? Now, whenever you do a chair flip, one thing that's important to remember is that the relative positions of substituents are going to change. Okay? Let's take an example. All right? Let's take a look at something like this. This is methyl cyclohexane. It's just cyclohexane where one of the H's has been replaced by a CH3. All right? If I wanted to represent this in a chair conformation, right, I can just pick any one of the carbons. Doesn't matter which one, because no matter which carbon I put it on, again, nomenclature, by definition, it's number one. I usually like to pick the end carbons to work with whenever possible. So I'm going to just go ahead and draw the axial and equatorial bond on the end carbon, and I'm going to call that carbon number one. Also, we got to figure out, where do we put the methyl group? Do we put it axially or equatorially? Guess what? It doesn't matter, at least not in the first structure. It's entirely arbitrary. I'm just going to go ahead and put it axial for right now. All right? So that would be one of the chair conformations. All right? We can do a ring flip. Come on. He's being stubborn. There we go. We can do a ring flip. And let's see what happens. Whenever you do a ring flip, axial groups and axial bonds become equatorial, and previously equatorial groups and bonds become axial. And we can see that with methyl cyclohexane. All right. Again, let's take this end carbon, carbon number 1, and let's go ahead and draw the axial and equatorial bonds. Well, once we did a ring flip, now we know that this is a down carbon, right? So the axial bond should point down, and the equatorial bond should slant up. All right. All right, so when we bend it down, basically what was already pointed down here, the H, right? In the first structure, we had an equatorial H slanted down. That's now going to become your axial group. It still points the same direction, right? It still points down, but now it points down in the axial direction. Conversely, your methyl group, right, which was pointed up axially, now is going to point up equatorially. Okay. So practice that a little bit. You know, the drawing, of the backbone skeleton really doesn't vary at all. Every time, no matter what you have on it, you have one chair conformation and the other. What you do have to get the hang of is remembering where your groups are going to point after you do the ring flip. Okay? All right. Now, one other thing that's kind of interesting about this is that if you remember when we did Newman projections, we saw that not every Newman projection had the same stability or energy, right? Some of them were more stable than others. The staggereds were more stable than eclipsed, for example. This is actually something that you also see in chair conformations. These two guys are not equal in stability, and in fact, because of that, the equilibrium will actually favor one side over the other. And I'll tell you, the group that it favors is going to be the one on the right. That's because the bigger group, the CH3, in this case is equatorial. You have, whenever the bigger groups are equatorial, we have higher stability. Oh, I had to draw my Y like that. How embarrassing. Seriously, I write like a kindergartner, and it's even, when I write on a tablet, it's like I write like a preschooler. So please overlook my incredibly poor penmanship here. But you guys get the idea, right? This guy is definitely going to be more stable. Why is that? Well, if you remember, when we talked about Newman projections, we mentioned something called steric strain, right? That basically refers to crowding that can occur, right? Whenever you have larger groups like this methyl group that are axial, what can happen is they can sort of bump into these other axial groups, in this case hydrogens, that are sticking up from other carbons, right? These are close together, right? Whereas that doesn't happen over here. These H's are pretty far away from this methyl group. So you don't have to worry about bumping into them. These hydrogens have a name, by the way. These are referred to oftentimes as flagpole hydrogens. And the specific steric interactions are usually called 1,3 diaxial interactions. And those give steric strain, crowding. Okay? So, whenever you're trying to figure out which chair structure is more stable, which one is more favored, it's always going to be the one that has your biggest groups off on equatorial bonds. Okay? Hopefully that makes sense. If not, please let me know, and I'll be happy to try to explain it further. All right? All right. Let's take it a little bit further. Let's try to put two substituents on a ring. All right? Let's say we had this. Say we had two methyl groups. All right? Well, first of all, before we even get to the chair conformations, I want to introduce a new way of drawing some of these, even on just the planar structures. All right? I'm going to show you how to draw three-dimensional bonds. All right? For example, let's say this top methyl group. It was coming at you from the board. It was pointing out of the plane coming towards the front. To represent that three-dimensionally, to represent that on a drawing, you would draw a wedge like this. All right? Let's say the bottom one's doing the same thing. You might have something like this. I apologize, by the way. You might hear the dogs barking in the background. I'm trying my best to ignore them because they're being total jerks right now. Anywho, you see in this case, both of these substituents are on the same side of the ring. They're both pointed on the front side. All right? Whenever they're on the same side like that, that is referred to as a cis arrangement. However, you might not always have a cis arrangement. You might have one of them coming out front, but the other one actually pointed in the back of the ring. That is represented by a dashed line, like that. And this is referred to as a trans arrangement. Okay? So, and you're going to see cis-trans in a couple of different contexts here. Within a context of a ring, cis means that the substituents are on the same side. Trans means that they're on opposite sides. All right? So we can represent that with the hexagon structure, but we can also represent this with chair conformations as well. All right? So let's try to draw a chair conformation. Well, first of all, to draw a chair conformation, we need to know whether we're drawing it for a cis or trans. All right? So let's just clarify here. Let's say that we're drawing the chair conformations for a cis arrangement. Okay? So in this case, we have two methyl groups. They're on opposite carbons, carbon number 1 and carbon number 4. So what I can do is I can just simply do this, work with those two carbons. One of them will be carbon number 1, one will be 4. I draw my axial and equatorial bonds. All right? So I know on this carbon, the carbon on the far right, the first placement is arbitrary, right? So I'm just going to put the CH3 up here and the H over here. Now we need to place the CH3 and the H on the other carbon. And this time it's not arbitrary because we want specifically a cis arrangement. Okay? Cis arrangement means they're both pointed in the same direction. That means either up or down. Cis and trans, I want to emphasize it. Cis and trans does not have anything to do with axial equatorial. A lot of people make that mistake. Cis means that they both need to be pointed in the same direction. So, if we need the other CH3 to point up, that means we have to put it on the equatorial bond because it's slanted up. And then we can draw our H. Right? So this is one of our cis conformations. All right? To draw the other one, you can do a ring flip. Like that. All right? Keep track of your carbons and your bonds, right? So we have a down carbon now. So axial down, equatorial up. The H was pointed down equatorially. Whoops, stray mark. H was pointed down equatorially. Now it's going to be pointed down axially. CH3 was up axial. Now it's up equatorial. All right. Go to the other carbon. Axial bond, equatorial bond. CH3 was up equatorial. Now it's going to be up axial. H was down axial. Now it's going to be down equatorial. And Viola, you have got your 2 chair conformations for the cis arrangement. Now, here's a question. Which one of them is more stable? Which one of them is favored? Right? Well, golly gee, you have a conundrum here. Structure number 1 has one big group axial and one big group equatorial. So does the second one. So guess what? Neither one of these is favored. This is a perfect equilibrium between the 2 structures. Neither one of them is favored. Okay? So, those are the 2 chair conformations for the cis arrangement. Now, we can do the same thing for the trans, right? All right, so I could draw a chair conformation. I'm going to draw my bonds, and then I'm going to fill in the blanks. Come on. There we go. All right, so again, I'll just start with CH3 over here. All right. Now, this time they're trans. I want the 2 methyl groups to point opposite. I've already got one pointed up, so I need the other one pointed down, which means it's going to be equatorial. Excuse me, axial, sorry. We do a ring flip. We saw last time that when we do a ring flip, we get this. All right, the other carbon, methyl group was down axial, now it's down equatorial. H was up equatorial, now it's up axial. All right, and there we go. There is our last chair conformation for 1,4-dimethylhexane. Let's see. Is either one of these structures favored in this equilibrium? This time I would think that you should hopefully see that yes, obviously the one on the right is definitely favored because both large groups are equatorial, whereas in the first structure, they're both axial. And in fact, if you're asked, and you very well might be, asked a question like this, you might be asked to say, out of these 4 structures, which one of them is the most stable? And hopefully it should be apparent to you that that one is definitely the most stable one. All right. Very, very good. Let me do one more, just as an example here. I haven't drawn anything on the middle carbons yet, so I feel like I should do that because people get kind of scared of drawing stuff in there, but it's fine. Let's say we wanted to do this. Let's put a couple of halogens on here. Let's put them at 1 and 3. Now, we actually haven't seen halogens yet as substituents as far as nomenclature, but we will later on. But if you hear me refer to these, Br is going to be a bromo, Cl is going to be a chloro. All right, and let's see. What do I want to do this for? Let me think for a second. Let's try this in the cis arrangement. Okay. Well, again, you could actually, go with a number of different arrangements as long as you had them, on carbons that would be 1 and 3 to each other. Again, I always like to make one of them the end carbon at least because, it's a little easier to work with. So I'm going to make that one look like that. Now, I could go either clockwise or counterclockwise here to get to a carbon number 3. I'm going to go counterclockwise, so I'm going to make this one carbon number 3. Okay, and since it's cis, oops, that's not right. We would have that. Ring flip. That's ugly. Sorry about that. So I have a harder time drawing the reverse chairs for some reason. I don't know why. Mental block. Plus, I'm a terrible drawer. So, all right. So we do a ring flip. The H is now going to be down. BR is going to be up equatorial. All right. Cl and H are over here on this carbon. There's our axial C8, or excuse me, axial H pointed down. And oh, this is going to be hard to draw. This is a very poorly drawn equatorial. I feel the slant should be better, but that's the best I can do with my poor drawing skills. But you get the point, right? It was up axial, now it's up equatorial. Again, hopefully it should be obvious that this one is way, way favored over that one. Okay? So that was the cis. Let's draw the trans now. All right, so draw our first one. Again, I'm just going to stick the BR and the H here like this. All right. Now they're on opposite sides, so I need that CL to point downward. So it's going to be slanted down equatorially, and the H will be axial. All right. Do a ring flip. We get that. And for the other carbon, we'll have a Cl pointed down axially, and the H equatorially off to the side. Now this one's a little bit different because now we have to decide again which one of these two is going to be favored. All right. Now it was easy last time because we were using groups of atoms. CH3 obviously is going to be bigger than H's, right? But now you're looking at two individual atoms, Br and Cl, right? Well, don't forget, even if they're individual atoms, you can still have size differences, right? Use the periodic table and figure out which one of these is a bigger atom. If you remember your periodic trends, you get bigger as you go down a column. So the Br is the biggest group in this structure. Okay? So if you're looking for stability, you're going to get better stability when this Br is on an equatorial bond. The Cl is axial here, which is not ideal, but it's better than having the Br axially. So the equilibrium would favor the right side. Okay? All right, so that's a good introduction to chair conformations. There's lots of good practice problems in your book, so please be working on them in advance of your exam because you definitely will have questions about drawing chair conformations. This seems like a good place to stop the video, but I have a couple of other things, and it's so short, I really hate to bother making another video, so I'm just going to tack them to the end of this video. They have nothing to do with chair conformations or Newmans. They actually have to do with reactivity. All right? We're going to define actually, you know what? I am going to end this video here. Sorry for the confusion. I need to call my wife back. I'll make a separate short video for the rest of it. Until then, have a great afternoon.